Okay, hi everyone. It's great to be back here at Q2B. My talk is called Quantum Algorithms in 2024, How Should We Feel? This image here is how ChatGPT feels, but how should we feel? So I want to start by going back to the sort of picture of quantum algorithms that started to come into focus in the mid-1990s. So BQP, bounded error quantum polynomial time, is the class of all the problems that are efficiently solvable by a quantum computer. And so what did we know about it by then? We knew it includes classical P, all the problems that are efficiently solvable by a classical computer. The question that really interested us was, does it contain more? In particular, how far can quantum computers go at tackling the hard problems in the class NP, which is all the problems for which a solution could be efficiently verified or recognized. Okay? And of course, the great discovery by Peter Shor in 1994 was that there were certain very famous problems in NP that we don't know to be in P, such as factoring and discrete log, problems that we happened then as now to base the security of the world's internet commerce on, which are in BQP. Okay? They have quantum algorithms to solve them, thereby providing very solid evidence, having nothing to do with simulating quantum mechanics itself or whatever, that BQP is larger than P. Okay, they are different classes. Okay, but the holy grail in theoretical computer science for more than half a century has been what we call the NP-complete problems. Okay, these are, in a sense, the hardest problems in NP, the hardest verifiable problems. Okay, and that includes, most of what, let's say, people at this meeting might care about in, industrial optimization, in finance, in optimizing the parameters of a neural net, all sorts of things of that kind. Okay? And for NP-complete problems, we learned by 1996 that Grover's algorithm could solve those problems usually in about the square root of the number of steps that a classical computer would take. Okay? And that's super interesting and impressive, but that's not an exponential speedup. Right? It's turns an exponential into a milder exponential. Okay? And if you incorporate the enormous overheads that it will take to run a quantum computation fault tolerantly, then you get estimates that you would really need enormous problem sizes before the square root speedup from Grover becomes a net win in practice. Okay, so we then as now sort of did not expect that there would be an exponential quantum speedup for arbitrary NP-complete problems. Of course, we can't rule it out. We can't even rule out that P equals NP, as you may have heard. Okay, but it would have to be something unlike either Shor's or Grover's algorithm, or any of the other quantum algorithms we know. And for that matter, there are even NP intermediate problems, ones in this twilight region, like graph isomorphism or lattice problems that we don't know fast quantum algorithms for either. And for that very reason, these problems are what we're now basing the hopes on for post-quantum or quantum-resistant public key cryptography, particularly the lattice problems. Okay, now, just like we don't know if NP is contained in BQP, we don't know if BQP is contained in NP. Okay, and so problems of simulating quantum systems might give us examples of problems that quantum computers could efficiently solve, but where classical computers could not even efficiently recognize a right answer, let alone finding it. Okay, so this was the picture 30 years ago, and now what has happened since? Well, what's happened since is, many, many thousands of papers have been written clarifying every aspect of this picture, extending it into new directions to more problems, and yet I would say the basic picture has stood. Okay, has remained, remarkably stable. okay, even as we've filled in so many of the details of it and discovered new things. Okay, and so now the question to come back and ask it is, how should we feel about that? Okay, well, of course, how should we feel is not a question about the algorithms itself. It's a question about us, about our emotional state. And, different people might be in different emotional spaces and, therefore need different kinds of advice about this. But let me try to be a therapist here and say, what are some of the emotions that I often see in, 20 years of blogging and giving talks about this stuff. So one emotion that I very frequently encounter is what I call Rumpelstiltskinism. Okay, it's another nice chat GPT creation. Okay, but it's the attitude. Okay, look, you've spun this much straw into gold, so now spin more. Right? You have quantum algorithms that get exponential speedups for factoring and discrete log. Great. Now do graph isomorphism. Now do NP-complete problems. Now do machine learning problems. Sort of arbitrary ones. Do financial portfolio optimization, and that should just be our expectation. That breakthroughs on the scale of Shor's algorithm should just be an every year or two occurrence. Okay, now the flip side of that, if the Rumpelstiltskin thing doesn't get delivered, is defeatism, right? You say, okay, well, quantum algorithms looked like this amazing thing 30 years ago that could get all these exponential speedups, but it turns out to be incredibly specialized. It turns out that if you want an exponential quantum speedup, you need some very, very structured problem, with structure coming from group theory or number theory, for which you can somehow choreograph a pattern of interference that will concentrate all the amplitude on the answer you want. And that's just a very special thing. We should be, grateful that there are any exponential quantum speedups at all, like, for anything other than just simulating quantum mechanics itself. And we shouldn't hope for any more. Okay, so the question that I want to ask is, can we chart a middle course between Rumpelstiltskinism and defeatism? Can we explore the possibility of new quantum algorithms that go beyond the paradigms of Shor and Grover without sort of having an expectation that the universe has to deliver that to us? Okay, so of course, there's been a lot of research activity over the last 25 years on the potentially quantum accelerated versions of heuristic optimization methods, methods around simulated annealing or random walks or things like that. So a seminal result from 2002 showed that there were certain kinds of graphs for which a quantum walk can reach a designated end vertex exponentially faster than any possible classical walk. Okay, those graphs look like this, like these two binary trees that are connected by a random matching. Okay, I don't expect those kinds of graphs to arise very often in practice. Okay, but you can often show exponential speedups for other problems just by embedding this graph into those problems. And in fact, something like that was done just 4 years ago when there was a theoretical breakthrough about the adiabatic algorithm, which of course has been studied since the late 1990s, which is sort of the quantum enhanced version of simulated annealing. And we now finally know that at least in the black box setting, there are fitness landscapes where the adiabatic algorithm will reach the global optimum exponentially faster than any possible classical algorithm. It comes from work by Matt Hastings and then Gillian and Vazirani. Okay, but again, it requires creating these bizarre solution landscapes that you wouldn't expect to arise in any actual practical optimization problem. And so the question of are these exponential speedups relevant to the kinds of optimization problems that would arise in practice still stands, right? It might be that for those, for the practical instances, you only get the Grover type speedup. So there's also been a lot of excitement for the last decade about this QAOA that Ed Farhi and his colleagues have been very aggressively advocating, and the challenge there is to figure out is there a big quantum speedup that you can get with these kinds of algorithms for anything that we care about. I mean, people like it because it's low depth, meaning you could plausibly implement it on a near-term device, but it's not satisfactory to just have like thousands of papers about we can use QAOA for this or for that and not address the question, but are you actually beating what a classical algorithm could do? And so there is some recent empirical evidence that for some optimization problems, QAOA seems, just by looking at the empirical graphs, to get a polynomial speedup, which may even be a super Grover speedup. Okay, I would say we don't have evidence that QAOA is going to get an exponential speedup, at least for anything that we would care about, right? For sampling tasks, like as in the quantum supremacy experiments. Yes, there's an exponential speedup, but of course we want the speedup for a practical problem. Okay, so now 15 years ago, I introduced a task called Foration. When I was not thinking about any practical application. I was just looking for what is the task that would most distinguish quantum computers from classical ones, in a sense. Okay, and so Foration is the problem where you are given access to two Boolean functions, let's say f and g, and your task is to estimate this quantity here, which basically measures the correlation between the first function and the Fourier transform of the second function. Okay, hence Foration, right? Is one function, or you have these otherwise random-looking functions, and now you want to know, is one of them close to the Boolean Fourier transform of the other one? Okay, here's an instance of Foration. I don't expect that you can solve it by glancing at it. Okay, this is something that a quantum computer can do incredibly fast. You basically just query the first function, Fourier transform, query the second function, and then that's it. Okay, super easy quantum algorithm. But I conjectured that this problem not only, but does it take exponentially many queries for a classical computer to solve? That was pretty easy to show, but that it's not even in the polynomial hierarchy. Okay, and that was finally proven 6 years ago by Ron Raz and Avishai Tal. And if you don't know what that means, you can think of it as saying that this problem would still plausibly be hard for a classical computer, even if p equal to np. Okay, so and now building on that, this problem has been used for a bunch of other things in quantum complexity theory. So my spectacular former student, William Kretschmer, and others have now shown that you can construct public key cryptosystems involving quantum states, as the ciphertext, which would plausibly be secure even in a world where p equal to np. Okay, which is something that we just cannot be done with classical cryptography, and that all depends on Foration. But in terms of just straightforward algorithmic applications of this problem, we don't know any yet. Okay, and I love to give this problem out. Can you find some real-world task where you have two functions and you need to know is one of them correlated with the Fourier transform of the other? And you can't solve it classically fast. Because if you have such a problem, I mean, tell me. Because I have just the tool for you. Okay. So now since 2008, there was a lot of excitement about could there be big quantum speedups for machine learning problems. A lot of this started with the HHL algorithm, Harrow, Hasidim, and Lloyd, for implicitly solving a system of linear equations in only logarithmic time. There's also proposed quantum speedups for estimating Betty numbers, okay, which are some invariant and topological data analysis. Okay, but again, it's not clear whether the things that these algorithms do, as impressive as they are a good match for the things that anyone in ML would care about in practice, right? Sometimes this is because the algorithm gives you, an output that is itself a quantum state. as with HHL. Other times it's because the estimate that you get just has an enormous additive error, as with the algorithms for estimating Betty numbers. And other times we get a quantum algorithm that seems to get an exponential speed up that evades all those objections, as for example Karanides and Prakash did in 2016 when they proposed this beautiful quantum algorithm for recommendation systems, like the type of problem that Netflix solves. Okay, but then Ewin Tang, who was then an 18-year-old undergrad working with me, managed to dequantize the Karanides-Prakash algorithm, okay, give a classical algorithm with comparable performance. And now building on that, many of the other quantum machine learning speedups that we knew have been Ewinized, have been, dequantized away. And so I think it remains a huge challenge. Find an end-to-end speedup for a machine learning problem that we care about, and it doesn't count if you just embed an exponential quantum speedup that we already knew, like that from Shor's algorithm or from the glued trees, into your machine learning problem. Because then that just leaves the question, okay, when would that ever arise in practice? It has to be something that would arise in the wild. So now, I'd like to finish by talking about a breakthrough a couple years ago. It started by work by Yamakawa and Jandry. And I think, it was sort of the most exciting development in quantum algorithms in some number of years. And, once again, Yamakawa and Jandry were not asking, about, how do I solve some practical problem faster, right? They were asking about just what are the in-principle limits of quantum speedups at all. And they discovered a new task, which was, you're given access to, say, a random Boolean function, and now you have to output a list of n-bit strings. Okay, so n squared bits in total. And you want n different n-bit strings, where first of all, each of those strings maps to 0 under your random function. But second of all, when you concatenate those strings, you get a code word of some particular error correcting code. Okay. I told you that this was not going to be a practical problem in itself, okay? But amazingly, they showed that there is a fast quantum algorithm to solve this problem, to find an n squared bit string that satisfies both of those conditions, okay? There in general will be exponentially many such strings. They gave a quantum algorithm that finds one of them. They also showed that any classical algorithm would need exponentially many queries to f in order to find such a string. Okay, so that gave a separation, and not only that, it was a separation that solved an open problem that I and others had asked. Okay, they gave the first example of an NP search problem based on a random oracle, so not a structured oracle like those arising in Simon's problem or Shor's period finding problem, but a random oracle where quantum gives you an exponential speedup. Andras Ambayanis and I have had a conjecture for 15 years that you could never get an exponential quantum speedup relative to a random oracle for a decision problem. But then, some people ask, well, what about for a search problem, with many possible valid answers? And we said, yeah, I guess that's a loophole in our conjecture. So basically, Yamakawa and Jandry drove a truck through that loophole. And now building on what Yamakawa and Jandry did, just this year, Stephen Jordan and his collaborators have given a new quantum algorithm that actually solves an NP-hard optimization problem with a better approximation ratio than we know how to achieve classically. Okay, so now we are getting closer to something practical. Okay, the problem that they address, where they get the most impressive speed up, is something called optimal polynomial intersection, or OPI. Okay, and it's basically you're given a bunch of subsets of a finite field, and now you have to find the polynomial of some fixed degree that intersects the maximum number of those subsets. Okay, as you see in this picture. So this is an NP-hard problem. And their quantum algorithm, based on Yamakawa-Jandry, gets like a 0.7 or something approximation for this problem, whereas classically we only know how to get 0.55. Okay, so it's it's the only example, I think, that now stands of a better approximation ratio quantumly for a natural NP-hard optimization problem. And now the way that they did this, in some sense, was by exploiting the fact that there is all this algebraic structure in this problem related to, Reed-Solomon codes and things like that. And, their algorithm is complicated, but at the core of it, ultimately, it uses a quantum Fourier transform, just like Shor's algorithm did all those years ago. Okay, so, by just going back to algebraic structure, but looking for it in NP-hard problems, we can do something. So how should we feel, to summarize? Well, I'm feeling pretty good right now, but the secret to feeling good is low expectations, right? Then anything that comes along, like this DQI algorithm, is going to make you pretty happy. For me, the #1 application of quantum computing remains refuting the people who said quantum computing is impossible, like Gil Kalai, who continues to say it's impossible even after the Google Willow thing. So I redouble this statement. Everything else is just a bonus for me. Okay, and so let's look for those bonuses, and then it's even better. Right? But Yamakawa and Jandry and its offshoots, like DQI, remind us of just how much remains to be discovered about the limits of algorithms, both classical algorithms and quantum algorithms. I would also say that if we want it to be humans and not AI that discovers the remaining quantum algorithms, then maybe we should get cracking now. All right, thanks for listening.